Welcome to class. We're officially beginning the course. I'm going to begin with a quick review of some of the things we've done the other day, and then we're going to push it forward. We discussed what are functions, and we started focusing on what we call linear functions. Functions, as we said, are just basically relations between variables, sometimes between many variables. But for our course, it's going to be between two variables, one input and one output, or one independent variable, one dependent variable. So think of the example I gave you was, like your brain. You ask somebody a question, and they process, and then they give you an answer. So your brain would behave like a function. Or if you put, 4 quarters in a soda machine, it processes. You even literally hear noise, and then a can of soda comes out from the other side. And sometimes the relation is very boring. You could dump in a number called 5, and you get 5 back. It's called an identity function. It's like y equals x. The input is the output. It can be boring sometimes. Okay. Now, we talked about the type of functions, and we said there are 2 types of functions that we deal with, and there is one type which we actually disqualify to be functions. The best functions are what we call one-to-one functions. For every input, there is only one output. And for every output, there is only that input. So you can go back and forth between the inputs and the output, or between the independent variable and the dependent variable. So that's why I put the arrow both ways, okay? The concrete example I gave you the other day was, you have a mailbox. Your friend has a mailbox, a different mailbox, and your mom has another mailbox. Everybody has a mailbox. This mailbox refers to you, and you are connected to that mailbox. So it's one-to-one. These are the best functions, as you will see in future math courses. The next best functions, or the next type of functions, are many-to-one. So it's possible to have many independent variables for one single dependent variable. And the example I gave you was if you visit an office or a hospital or something, they might ask you a number of questions at the entrance. What is your name? Show me your driver license. How old are you? How are you connected to such and such? So you give me this ID, that ID, right? And then they will give you one output called, let's say, the room number of the person you are visiting. These are functions, okay? So don't disqualify them. They're just not the best. Why? Because you have many to one, okay? So the example of the mailbox is, so you and your sister and your mom and your brother and your dad, all of you have one mailbox, and that's okay. That's okay. It's still a function, not the best, still a function, okay? The next group is what we call non-functions. So we don't like these at all. That doesn't mean they're not important, okay? They're actually, some of them are the best, extremely important, like circles. Circles, let me put circle here, okay? So you have one x and has this y, and the value of that x is this y. There are two y's. There are two y's related to that x. Now we know for a fact that circles are important, right? Circles are extremely important, but they don't qualify to be functions. So there are certain things we can do with this guys that we cannot do with this. But that doesn't mean these are not important, okay? All right. Now, a few examples we worked on very quickly. I'm not going to waste so much time. I said Costco hires you at $20 an hour, and I want to know the relationship between the variables. We decided that the variables have to be time and the pay. I call time t and the pay p. You've got to decide which is dependent on which. Clearly, the pay is going to depend on the time, right? If you work many hours, you'll get paid more, and so on and so forth. And you all told me that the pay is 20t. We decided to create a numerical table to explore the idea of the rates of change, okay? And we said if you don't work, you don't make money. And the points in blue is 0, 0. If you work for 1 hour, you make $20. Here you go. If you work for 2 hours, you make 40, and you can continue if you care. Now, we do this, number one, just to double check if this is correct. So if you plug in 0 here, you get 20 times 0, which is 0. If you plug in 1 here, you get 20 times 1, which is 20. And if you plug in 2, you get 40. So we know this is correct, okay? But the reason we did this is because we decided to figure out if the relation, if the rate of change is fixed. Well, you could see it just from the way it was explained to you. Costco hires you at $20 per hour. That amount of money per hour does not change, does it? That's a rate, isn't it? $20 per hour, that's a rate, like speed. 55 miles an hour. It doesn't change. So we know that the rate of change is going to remain fixed. What is that rate of change? Well, we said you take the difference of the y's. Let's look at these 2 points. You take the difference of the y's, 20 minus 0, divided by the difference of the input or the independence variable. So 20 minus 0 over 1 minus 0 gave me 20. But if I try these 2 points, I get 40 minus 20 is 40 minus 20 divided by 2 minus 1. I got 20 again. And if I try the first point with the third point, I get 40 minus 0 over 2 minus 0, which is also 20. So the rate of change is fixed. Therefore, we agreed that this relationship is linear. Why? Because the rate of change is fixed. Now, a question for you. You may want to pause the video and ask yourself, is this relationship, does it fall here or here or here? That's for you to answer, okay? So pause the video and think about it. All right, so welcome back. If I give you a particular time, is there more than one pay? So let's say I say you worked for 1 hour. How many pays can you get? Can you get 20 and something else or just 20? The answer is just 20. Now let's say I come to you with this scenario and I say, hey, I made $20. Is it possible that you have worked for 1 hour and some other time or just 1 hour? It's going to be just 1 hour. If you made $20, you would have worked for 1 hour. Every X gave me 1 Y and every Y gave me 1 X. So that qualifies here. So these are one-to-one functions. Generally, linear functions are one-to-one. I said generally because there are a few silly exceptions like a vertical line. Okay, so that's some of the best functions. They're simple. Linear functions are very simple, yet they are the best. Just like this one. These are not even functions. Circles are not functions, but they are important. Linear functions are silly, but they qualify to be some of the best functions. So let me quickly take you here and share with you the rate of change. And I do this for a good reason, and I'll explain that in a minute. So the rate of change has another name called the slope, as you probably heard, or what we call the multiplier. And the reason we call it the multiplier, because I'm very sure you have seen this form. Y equals mx plus b. It's called slope-intercept form. That m stands for multiplier, okay? That is your rate of change for linear functions. If it's not linear, there is no such thing as a rate of change. So it has many names. It's called the rate of change. It's called slope. It's called the multiplier. You wonder why? We call this m. It's called the change in y over the change in x. It has this notation, which reflects that change. Some people, even non-math people, when they're talking, they'll say, you know, my delta is, they mean to say my change is, right? The delta of the temperature was, people use this now loosely. So the delta just stands for change, okay? Which means if I have 2 points, I want to make sure you get this. If I have 2 points, x1, y1, and x2, y2, the rate of change is y minus y over x minus x, right? But if you decide to start with this point, you say y minus y divided by x minus x. You have to be consistent. You either go in this direction and say y minus y over x minus x, or move the other direction and say y minus y over x minus x. Make sure you begin with y's. Y's go to the top and the x's go to the bottom. What you're not allowed to do is to do something like this. Y minus y over x minus x. You were not consistent. Or say something like this. X minus x over y minus y. Kind of flip-flop these. You know, these are kind of errors sometimes people make. It's always the rise, the change in the heights, the rise, over the change in the horizontal distance called the run. It's not the run over the rise, it is the rise over the run. Sometimes you see this word when you're driving with your parents, and you may have heard this word in physics. So you're driving around some highway or whatever, back roads, and it says the grade is 8%. The grade is literally the slope, except that you're working in 3 dimensions. It looks something like this. So the road is like this, and you're climbing, right? You're driving up. So we don't call it the slope. We call it the grade. And if the slope is 0.08, they just call it 8%. It is always given as a percentage. So when you see the word slope, when you see the word grade, it just means slope, okay? It just means slope in 3 dimensions. Okay. So I'm going to come back to this page, but for now, it's just there are many ways to name the rates of change. Okay, so let's go back here. It turns out, as I'm sure you know, the number in front of your independent variable is your rate of change, is your slope. It's this. It's the number in front of your independent variable. If it is written in this format, y equals slope, rate of change, independent variable plus some silly number, which we will discuss later. That is always your slope. That is always your rate of change. So you know the rate of change is going to be 20. That's why it's here, that's why it's here, and that's why it's here. Okay? So quickly, the parameter of a rectangle. Well, you know the parameter of a rectangle is twice the width plus twice the length. But I gave you the length because I don't want to deal with 3 variables. I want to deal with 1 variable that is independence and 1 variable that is dependence. So I forced the length to be 20. So 2 times 20 is 40. I made a small mistake here. Let me erase it. This is 40. Okay, now, clearly, we said the parameter is going to depend on the width of the rectangle. So P is 2W plus 40. That kind of resembles this relationship. P equals something W plus something, right? So that is your independence variable. That's your X. That's your Y. That's your slope. That is exactly your slope. And that is just some number for now, okay? So the rate of change is just 2. See how quickly you can see it? Don't worry about 40 for now. Now, I gave you this for a good reason. The area of a square. So the side of the square is S. That's my independence variable. The area is the dependence. You know this from 3rd grade or 4th grade. The area is the square of the side of the of the square. And now I want to know if this is linear. Well, according to this, it doesn't look linear. We haven't discussed it in detail, but for now, it doesn't seem to be linear, but I want to make sure. So what do? I make my points. When S is 0, the area is 0. When S is 1, 1 squared is 1. And when the side is 3, 3 squared is 9. So here are my 3 points. Now, let's see if the rate of change remains fixed. Well, if I look at these 2 points, I do 1 minus 0 over 1 minus 0, which is 1. But if I use these 2 points, I get 9 minus 1 over 3 minus 1, which is 4. I could stop right there. The rate of change is not fixed. So I know for a fact that this relationship between S and A is not linear. Now, just for fun, I decided to also use these 2 points. You don't have to, okay? The moment they don't match, you could stop and say that the relationship is not linear. Now, if they do match, you have to continue, right? Because all of them have to match. So just for fun, I'm going to try the first points and the last points. 9 minus 0 over 3 minus 0. And that gave me 3. None of them actually. They're all different. Now, if this was 4, you'll be happy with these 2, but this one violates them. If this turned out to be 1, so those 2 are good, but this one violated the relationship. All of the values that you get must be equal. Now you can imagine that this is not an efficient method. I want you to pause the video and think about why this is not efficient. You know what I've been doing so far? This and this is not efficient at all. Why? Pause the video. All right. The reason it's not efficient, and I can't hear you, of course, so I'm going to assume this is what you're thinking. I'm only working with 3 points. What if I have 20? How many combinations of pairs am I going to try? Because all of them have to match. It's not efficient. It's not wrong, it's just not efficient. So we don't want to rely on creating a table and look at all combinations of pairs. It's just silly. I mean, even if I have just 5, there are a lot of combinations. The first with second, first with third, first with fourth, first with fifth, and then second with third, second with fourth, second with fifth, and so on and so forth. It takes forever. So the trick, of course, is to recognize them on the spot without having to resort to numerical tables. And the idea is this. It's very simple. You have a dependent variable and you have an independent variable called x. And let's say I have something like this. I'm going to give you like 3 examples. Okay. You see, the independent variable here has an exponent of 1, and the dependent variable has an exponent of 1. So this qualifies to be linear. Even though this is 1, this is not 1. So this is not linear. So both have to be 1. This is 1, that's fine. But square root of x, as you may know, it's x to the half. So that's not good. Okay? So what you want to do is, if you are able to isolate y, have y by itself on the left-hand side, if you can find some number x plus or minus some other number, that is linear. In other words, if it looks like this, I highlighted my variables in black. These are just numbers. That's the rate of changes, you know. This one we don't know yet. That is x to the 1, and that is y to the 1. So that's how you quickly realize whether or not the function is linear. So if you look back here, 1, 1, linear. 1, 1, linear. 1, 2, not linear. Very quick, right? So I'm going to conclude with a harder problem. So I want you to pay attention. By the way, I didn't say that these are not important tables. I'm just saying they're not efficient to find the rate of change. They can be very helpful in figuring out the function. You kind of know this off the top of your head. You kind of know this off the top of your head. When I said, you know, you work at Costco at $20 an hour, everybody told me P equals 20T. Now watch this one. The table is going to be very helpful to me, not to figure out whether or not the rate of change is fixed. It's because it is so difficult to come up with a function. And therefore, when you are stuck, if you don't know how to deal with the relationship, you do want to create a table. So here is the situation. Your teacher decides to add 1/4 of all missed points on your test. Okay? And let's say the test is over 100 points. So maybe students didn't do well. You know, they just crashed the test. They didn't do well. And the teacher says, hey, whatever you missed, I'll give you a quarter back. For example, let's say you got 60 out of 100. It's like, okay, you missed 40. So I'm going to give you a quarter of 40 back, which is 10. So now 60 becomes 70. Makes sense? So let's work out some examples, some points first. Let's say you got 0. Hopefully nobody in the world gets 0. But let's say you get 0. So you missed 100. You missed all of them. So what is 1/4 of all of them? That's 25. So if you got 0 on your old, I put this in quotation mark. I don't want you to confuse this with 0. That's O. O stands for old. Okay. So my old score is my independence variable, and my new score is the dependence variable. Of course, the new score is going to depend on the old score, right? Everybody, kids didn't do well, and we're going to change your score into a new score, so the new score depends on the old score. But I don't know how to write the formula, so please don't look at this yet, okay? So I'm going to create a numerical table. So one extreme is if you get 0. If you get 0, that means you missed 100 points. So we're going to give you a quarter back. A quarter of 100 is 25. So 0 gives you 25. This is the most anybody can get, by the way. You jumped from 0 all the way to 25. You will never get this later. Let's go to the other extreme, which is this guy. Some person got 100 out of 100. So they missed 0 points. So they get a quarter back of 0. Well, a quarter back of 0 is still 0. So they keep that 100, right? 100 plus 0 is still 100. So this guy, this person, this lady got nothing. This person got the most, by the way. So let's look at a typical student, got 80. Well, this student got 80. So that means they missed 20. A quarter of 20 is 5. So now their score is 85. So they gained, this guy gained 25. This guy gained 0, nothing. And this guy gained 5 points. When I say guy, I don't mean a boy, okay? I'm just speaking loosely. Person, students, girl or a boy. All right. The other one I did earlier was 60, right? If you got 60, you missed 30. And no, you missed 40. And a quarter of 40 is 10. So now you have 70. You got 10 points back. Make sense? Why do I create this numerical table? Because it's going to help me find a function. First, let's just make sure that the rate of change doesn't change. You're going to say, Mr. Alam, you told me not to use table for rate of change. Yeah, but I don't have the function. I don't have this yet, okay? Don't look here. So let's see if the rate of change changes. 85 minus 25 over 80 minus 0 is 3/4. 100 minus 25 over 100 minus 0 is 3/4. 75 over 100, which is 3/4. I'm happy. Let's look at this one now, these 2 points. This point and this point. 100 minus 85 over 100 minus 80. The rate of change does not change. Therefore, the relationship is linear. That's the good news. The bad news is I don't know the function. Well, I can figure that out easily. We just decided earlier that we said if it is linear, it looks something like this, and that is the rate of change. Isn't that true? Well, you already know the rate of change. It's 3/4. So you just sneak it in there. That's X or old. That's Y or new. So we already know this number. So that leaves me with, what the heck is this? How do I come up with this number? Do I just steal it from somewhere? Where did it come from? Okay, so that is called the y-intercepts, or the initial value, and I'll explain. Imagine x is 0. If x is 0, m times 0 is 0, and 0 plus b is b. So when x is 0, y is b. That is called the y-intercept. Isn't that true? When x is 0, y is b. It's called the y-intercepts, or initial value. Why do we call it initial value? Because if you, initial value means initial anything, like initial slope, initial number of points, initial height, initial weight, initial capital to start a business, initial time, initial anything. So initially meaning got 0 points. What is the y-intercept? 25, right? That's your initial value, 25. This came from here. When x is 0, what is the y value? I'll do it here. When x is 0, this is your initial value, called y-intercepts, called b, this b. So for linear functions, that's your independence variable, that's your dependence variable. If you know your rate of change, you're 50% done, because you need to know m and you need to know b. M and b have a name. We call them parameters. They're constants, but since we don't know what they are yet, we call them parameters. They're not variables, but they're not constants in the sense that this is 5, because I don't know what it is yet. So because you don't know what it is yet, we call them parameters. This parameter is the slope. We already identified that this has to be 3/4. And this is the initial value. The initial value comes from here. When x is 0, what's the y value? So that number goes here. And that rate of change goes here. And now you have the relationship. Okay? It should make sense to you, by the way, after a while. And I'll explain. Your teacher said, I'm going to give you 1/4 of all missed points. That means you're going to get 3/4 of the old score. Think about it. If your teacher gives you 1/4 back of anything that you missed, by definition it means your teacher gave you 3/4 of what you actually got, not of what you missed. 3/4 of what you got, old score. So this is kind of expected. I'll write it this way. Y is 3/4 x plus 25. 1/4 back of what you miss is the same thing as 3/4 back of what you have. So that's obvious. This one you just have to really think about it. Like initially, can anyone get anything below 25 on the new score? No. The worst case scenario is somebody who got 0, which means now their new score is 25. So you might be able to pull this just by looking at these statements. Clearly, this problem is much harder than the previous 3. So I'm going to give you a little homework. You don't have to submit it, but I really want you to think about it. Okay, I want you to try it by yourself. And you can ask me questions during conference. Can we write this in this format, because honestly, this is how I always think of it anyway. I'm saying, can we write the previous relation, which is this relation, in this format? In other words, can you convert this, here it is, new equals old plus 100 minus old over 4. Can you convert this into the one we just got? I put them in bold so you know that they are variables. This is not 0, that's old. Old, new. The reason I think about it this way is because I'm thinking if I'm giving a quarterback, a student's got a score, I give them a quarterback means what they miss is 100 minus old. So if they got 60, that means they miss 40. If they got 50, that means they miss 50. If they got 0, that means they miss 100. 100 minus 0 is 100. If they got 80, that means they miss 20. And I'm giving them a quarter. This is like 1/4 multiplied by this. A quarter of what they missed. Of course, I have to add it to the old score. See, that's how I think of it. Okay? I'll write it this way for you. It's so important to learn how to think analytically. A quarter of what you miss. This is what you missed. Isn't that true? That's what you got. That's what you missed. A quarter of that, which is essentially this. A quarter of what you missed, and then I'm going to add it to what you actually had. I'm not going to just give you a quarter back. I'm going to give you a quarter back in addition to what you had. So I believe this relationship is the same as what we just got. So I want you to pause the video and I want you to use a little bit of algebra and see if you can go from here to here. Stop the video, please. All right, I'm going to show you quickly how to get it. We discussed this already, right? We discussed this. So I'm going to show you how to get it quickly. So a quarter of what you missed plus what you had. This is the one I just gave you. So I hope you got it. I'm going to multiply top and bottom by 4 to have a common denominator. I put it in green. Then I combined the two expressions because there is a plus. They have the same denominator. So I'm going to combine them. It's going to be 4x plus 100 minus x, the whole thing over 4. Now 4x minus x is 3x plus 100 over 4. Now I'm going to split it now here. You know, you guys, I hope you know this. If I have a plus b over c, you can always write it as a over c plus b over c. I know students like to go this way, but you can also go back this way. I did it here by combining, but now I'm splitting because I combined these two. Now I'm going to split it right there. So it's 3x over 4 plus 100 over 4. 3x over 4 plus 100 over 4. That's 3/4 of x, and 100 over 4 is 25, which is essentially what I want to get, right? Isn't this the same thing as this? Okay. So I spoke a lot. I hope this was helpful to you. Feel free to review the video or slow it down or watch it again, and I will see you next time.